Shall we make a start? All right, we'll make a start. Thanks everyone for coming. I'd just like to start by acknowledging political people, the traditional owners of the land on which we're meeting. My respects to elders past, present, and any Aboriginal and Torres Strait Islanders in the audience. It's my great pleasure to introduce Tim Brownback, who many of you will know, all of you probably know. Tim is a Scientia lecturer in ICRR and also part of CCRC and also part of 21st Century Weather ARC Centre of Excellence. He wears many hats. He joined us last year. Prior to that, I was working in CCRC, and he's the man in demand about convective storms, hail hazards, and a bunch of other highly relevant and highly topical things, given the way the weather is changing right in front of our eyes, as Wes just went through. Cyclone Alfred can testify. So I'm really keen to hear all about changes in hail hazard in Australia.
Thank you very much. Thanks for being here and thanks for joining online. I hope you can hear us and see us. So yeah, I'm going to talk about changes in hail hazard. I'd just like to acknowledge the Aboriginal people also on whose lands we meet. And my work is partly funded by QBE, so I'd like to acknowledge that right up front as well. So yeah, I thought I'd start in Brisbane. Brisbane's been in the news a little bit recently. But here I want to talk about a different case, different storms in Brisbane of a different scale. So this was back in 2020 on Halloween, very spooky. And there was a big hailstorm that came across. And in fact, you can see there were multiple cells. So you can see them all right down here, heading straight into Brisbane, also Noosa. And this storm turned out to cost a really large amount of money. There was 14 centimetre hail. So that's really large. If, by the way, you ever collect any hail when you're outside and you have a hailstorm come across, please do include something for reference for scale. So these people have put a cricket ball and also a horse. So just make sure that you have something for scale. Someone said to me the other day, is that a horse or a pony?
That's a pony.
See? So try to choose something really scientific. So we had hail. It caused over $1 billion in insured damages, smashed right through people's roofs. I think there were cases where the hail went through solar panels, through people's tiles, into their kitchens, and it took a really long time to get fixed. There are still people there who are recovering from this storm even years later.
Sorry, someone's in the waiting room.
Yeah.
If you can.
Thanks. We might have to keep doing that, I think. So this wasn't the only storm that year either. So we also had, so there was the storm in Brisbane with 14 centimetre hail. There was also one in Rockhampton with 12 centimetre hail, also came with winds of 100 kilometres an hour. And earlier in the year, in January, there was the Canberra hailstorm, my hometown, which got smashed by hail up to 6 centimetres and also a wind gust of 117 kilometres an hour, which was a record. And all of these events cost a really large amount of money in insured losses. So both the Brisbane and the Canberra events were over $1 billion and the Rockhampton event was over $500 million. So these events really cost an awful lot of money. We also had the largest hailstone on record back in 2021 in October that was interesting because it was subtropical. It was up near Mackay, and this storm produced hailstones of 16 centimetres in diameter. That's really big. I've got a model on my desk of one of these, so if you want to come see one later, please come past. This stone here is actually not the largest. It's a 14.5 centimetre stone, but it's still massive. So we've got this really expensive kinds of events. They can produce a lot of damage. And it's not only in Australia, it's also around the world. Of course, you get these storms across. I just went through and found some articles. This slide took ages to make and I'm going to spend about 10 seconds on it. So it's just to say that there are storms across the world also. What a lot of effort. Hail losses.
It looks great.
Thank you. So these storms are really expensive. They make up a really significant proportion of natural peril losses. So here's a plot for Australia, produced by the Insurance Council of Australia. It shows the proportion of losses in normalised terms that by different perils. So you've got cyclone, flood, hail in light blue, other storms, fire and earthquakes, and then averaged over the last 30 years, 20 years, 10 years, and 5 years. So you can see that, first of all, hail is a really enormous amount of the overall losses. It's like a quarter. And it's also growing over time. So my job is to try to work out what climate change has to do with these changes and to try to talk with industry about how they can best respond and how we can best mitigate and adapt. So I'm going to split this presentation into 4 parts. I'm just going to give a background on climate change and hailstorms. Then I'm going to talk about some past trends. So looking back at the last 4 decades over Australia and how things have changed across Australia. Then I'll start to look into the future. I'm going to look at projections for Australian cities. First of all, for hail damage potential. When I'm saying damage potential, I really mean how large the hailstones are and how much wind comes with these storms. And then I'm going to try to go more globally and go out to the global scale for frequency of hail. So starting out with the climate change effects. And this is based on a review article that's now a few years old, but it had this great list of authors from, we had someone from every continent except Antarctica, and it was great fun to do this. Okay, so I'm just going to start with how hail forms. Yes?
Oh, no, sorry, you still got a couple in the waiting room, I think.
Yeah.
Okay, all good.
I'll let Alana deal with those. Hail forms in thunderstorms. So to get a thunderstorm, you need certain ingredients. We talk about atmospheric ingredients. I'm going to keep coming back to this ingredient idea. So to get a thunderstorm, you need a few things. You need an unstable atmosphere. And what that means is that the air low down in the atmosphere is warm and the air high up in the atmosphere is cold. And if a bit of that warm air gets into the air that's cold, it's going to rise like a hot air balloon and you get an updraft. So thunderstorms are all about updrafts. And you often need a trigger because if you have an atmosphere that's unstable, it can just sit there, like unstable, but nothing sets it off. And what you might need is a trigger. That could be a mountain, could be a front. What you need is something to mechanically push this warm air up into the colder air. That's the trigger. Then you get an updraft. So you get all this air pushing up and up and up into the atmosphere, and it brings with it moisture. As it gets higher in the atmosphere, it gets colder, the pressure reduces, you get condensation. So the moisture turns into clouds and then it can turn into rain. Some of that moisture is going to end up super cooled. So some of it's going to turn into solid ice and some of it's going to turn into super cooled liquid water. So water that's below freezing, but it's still liquid and it's just kind of hanging out up there, super cold, below freezing. If you get little bits of ice that are being blown around in this storm, the super cooled liquid water hits those bits of ice and freezes onto the outside almost immediately. And so you get the growing of the hailstones. So the longer an embryo, it starts out as an ice embryo, the longer an embryo spends in the updraft of the storm, the larger the hailstone can grow. So it's all about updrafts. So you get hailstone growth. Eventually, the updraft just can't hold it up anymore. It's too big. It's like a 14-centimeter monster. The updraft can't do it. It falls. And as it falls, it's going to fall into warmer air and it's going to melt. So these stones actually melt a surprising amount on their way through the atmosphere to get to the ground. And that's going to come into play later when we talk about climate change effects. And then it smashes into your car and so on and so on. So we've got a few different expected changes with warming. Here I've got a slide with the current atmosphere on the left and then a future climate that's warmer on the right. Okay, so here's a few changes. The warmer atmosphere can hold more water by about 7% per degree of warming. And so it's got more moisture in it, and that means more energy that can be released. So that means more instability. So you have this warmer atmosphere, it's more unstable, you can have more energy, stronger updrafts. Stronger updrafts might mean larger hailstones. But in a warmer atmosphere, you're going to have more melting. So you're going to have these small hailstones that get created in an atmosphere that's more unstable. You might have more storms, more generation of hailstones up high in the storm up here, but below this MLH, the melting level height, it's warmer than 0 degrees, and those stones are going to melt, and you might end up with those small stones just melting away. They just become rain. So you get more rain, but less hail. And another factor is vertical wind shear. So wind shear is just, you might hear about this around airports. Wind shear is where you have different winds by height. So you might have winds blowing this way at the surface and this way high. You might have winds blowing in the same direction but different strengths. by height. So that's wind shear. The more wind shear there is, the more the storm can become what we call organized. And it means that the more likely it is to start rotating, become a supercell that can really bring in more moisture from around it. You have the rain, instead of falling directly onto the updraft, including the updraft, the rain is shifted slightly so that the updraft can continue getting stronger without being killed by the friction of the rain. So the storm can become stronger. And in a warmer world, there's kind of this theory that vertical wind shear might become less strong, but when you kind of look into the details, that effect tends to get blown out by the effect of these other two, the moisture going up and the instability going up and the melting also going up. So you put all this together and you might end up with this idea that you could get fewer hailstones at the surface because more of them are just being melted away and most hailstones are small, okay? But you might end up with the stones that actually get to the surface being larger because you've got stronger updrafts. So that would give you the hypothesis of less hailstorms, but more severe hailstorms when they actually happen. That's the kind of hypothesis. But when you actually look around the world, you see that this is not the story in reality everywhere, and I'll talk more about this soon, that there are geographical differences, and so we still talk about really high uncertainty on these. So why is there high uncertainty? Hail's really difficult to observe, and it's really difficult to model. So you think in your life, how many hailstorms have you seen? Like actually been in a hailstorm? Has anyone seen more than 3, 4, 5? So you imagine you've got an instrument, you want to put it outside and collect 20 years of hailstorm data. You stick your instrument out there, you might get 1 storm in 10 years. Okay, so it's really difficult. So here's an example from a study a few years ago, Prine and Holland. They tried to do a climatology of severe hail, so that's hail over 2 centimeters. And look at the color bar, it goes up to 18. That's 18 days per year where you might get hail in a 100 by 100 kilometer area. That's the maximum worldwide. So it's really difficult to measure hail because it's rare and because it's quite a small process in the scale of things. You know, you might get a storm that hits the airport, it's not going to hit the suburb next to the airport. So it's small. It also makes it harder to model because it's small. Because the smaller your processes are, the more high resolution your models need to be and the more computational power you need to model those processes. So this is why it's difficult. If you were to try anyway, go, I know it's difficult, but screw it, I'm going to try it anyway. Here are some of the ways you might do it. So you could put out hail pads. These are like the lowest, the least complicated instruments I've ever seen. They're polystyrene sheets. You put them out in the hail, then someone has to go and collect them, and then you have to measure the holes that the hail made. So you then count up how many times it was hit. And this kind of thing people have done great work with these instruments. So the problem is the manual work that goes into having to collect them. You could use station data sometimes in countries like China, for example, shown here. They had this excellent network of stations where there were people who would observe, and they were trained and they would observe what happens and they would write it down. That was great. But as station guidelines get updated, sometimes the service that's running the network says, look, don't worry about hail less than 2 centimeters. It doesn't get recorded. Or in more recent times, the automatic stations are replacing people, and the automatic stations tend not to observe hail. So we're losing hail as time goes on. Or you could just use reports. So people often say to me, why don't you use Twitter? And Twitter would be great. People do put a lot of information on hail on Twitter. People also misspell the German word hail, and you get a lot of hits for, you know, hail this, hail that. So it's difficult. And reports are also biased towards non-meteorological things. So if you map the reports in America, for example, you see the highways, you see the cities. So it's where people are to observe them. And so it's very difficult to get report data to show you trends. People also overestimate the size of the hail they show. In Switzerland, they've got a great reporting service, and they have the largest size that you could possibly report, I think, is a tennis ball. In Switzerland, that doesn't happen very often, and it's designed to collect the reports. So that if you see that report, you go, no, it's not really real. You could use insurance data. The insurance companies have a really large amount of data, and it's great, but you have to be careful with it. Well, it depends on the objects that are insured, that change over time. So it's non-stationary and it tends to have coarse resolution. We often talk about suburb level or postcode level. So depending on what you want to do, that data can be tricky to work with. And then you get into the kind of stuff that I do more of, hailstorm ingredients. So if we can look at the ingredients for hailstorms, and that's what I'm going to talk about in a minute, we can talk about how the number of hail-prone days has changed. So instead of talking about the number of actual hailstones that you got on the ground, you talk about the ingredients. Or you can use simulations. As I said, they're expensive, but you can do great work using simulations that can really look in detail at the processes that are going on. All right, this is from the study. I'm not going to go into great detail here, but it shows a kind of summary of the studies that have occurred up until 2021 on hail frequency changes. I'll just make a very broad point. There are some regions that are not covered. Africa is basically not covered. And if you look at the colors, we've got blue for decreases, red for increases. And for example, across Europe, a mixture of different signals. So it's very difficult to make one kind of blanket statement about what hail is doing over past trends. And then if we look into future trends, the map is really empty. So there's a few studies in Australia, not very much, a few in Europe, few in America, and then we really don't know much for the rest of the world. And this is for frequency of hail, or severity of hail. Although the story is perhaps a little bit more simple because more instability means larger hail, we just don't have that many studies that kind of confirm that for future projections. So at the end of each section, I'm going to try to give a one-sentence conclusion or two-sentence. I wasn't able to do one sentence for some of them, but we expect hailstorms to be affected by climate change. And that's primarily because the ingredients that you need for hailstorms are affected by climate. We know this. But the details of how they will be affected change geographically, and so details remain highly uncertain. IPCC, for example, puts an uncertain sticker on these projections, and I think that's right. So now looking into some of my work on trends in hail-prone conditions across Australia. This was from the Canberra hailstorm, by the way, nice gum trees and hailstones. So this is a proxy study. So what I'm looking at is not hail itself, but the ingredients that lead to hail. And here's how these proxy studies tend to work. You say, to get a hailstorm or to get a big thunderstorm that could produce hail, you need a lot of instability, and we measure this using a thing called convective available potential energy. It's basically the temperature difference between an air parcel that's being pushed up and the environment around it. The hotter the air parcel, the higher the instability. And wind shear. You say, if I've got a lot of wind shear and a lot of instability, then it's hail prone. And if I don't have much of either, then it's not hail prone. And that would be the simplest kind of hail proxy that exists. In our study, we went a little bit further and we said, well, actually, hailstorms occur in different conditions. For example, in the tropics, you often have a lot of instability, but you don't get very much hail. The atmosphere is just very unstable. It's warm up there. And so you get a lot of this bubbling up of storms, but not very much wind shear. In the south, over Tasmania, you get a lot of wind shear, but you don't get a lot of instability. So what we did was we allowed this discriminator line, the red line here, to change depending on where we are. And my initial idea was to use latitude, just to kind of get the tropics and the mid latitudes, but I didn't want it to be a geographic feature. So instead we used the melting level height. The melting level height is high in the tropics, it's low in the further south you go. And so we allowed the importance of those different ingredients to change based on where you are and what the melting level height is. So it takes explicitly the temperature of the atmosphere into account. Now, when we apply this proxy over the last 4 decades, and here I'm using reanalysis data, which is like our best estimate of what the atmosphere was doing each hour over the last 4 decades. It's called ERA 5. So this is from 1979 to 2022. The degree spacing here is quarter degree, so we're at about 30 kilometers spacing. And I applied it at 3 hours each day, and you get a map that looks like this. So this is the mean number of hail-prone days per year over that period of time. And so this shows us kind of what we expect. The East Coast is where you get the most hailstorms in Australia. You have a a decrease over the elevated terrain. You don't get a lot of hail up there. You have a slight increase around Perth. This area is interesting because we don't really know exactly why there's more hail there, but there are other studies that show that as well. Same thing with Burketown, which you don't really see, but it's right up in the Gulf of Cafeteria. Seems to be a hail hotspot. We'll look more into that, but the population is super sparse, so it's difficult to know. Yeah.
So Tim, I just wondered, do you know the mapping between a hail prone day and an actual hail event? Is it like on average one for one, or is it like 50?
It's on average. So I'll show a plot later which shows that it's like 15 to 20% of the time you get a hail prone day, you actually get a hailstorm. Maybe 10 to 20. So it's not very much. Yeah. But what we did in this study was we thought, well, if you have a trend in the number of hail prone days, then you should also have a trend in the number of hailstorms. So what we also did was we looked at trends. So this is how those hail prone days have changed over the last 4 decades. So if you kind of squint from a distance, the map looks blue. We're getting an overall decrease in the number of hail prone days. But there are these red areas, and unfortunately for us, the red areas tend to be over the places where we've built massive cities. So we have red areas over Canberra and Sydney, should say Sydney and Canberra, because Sydney's a lot bigger, around Perth, and then down over Tasmania as well, although we don't get a lot of hailstorms in Tasmania to start with. So really, the main areas of interest here where we're getting increases are the southeast and the southwest. So just zooming in on those cities and now putting it in relative terms, we can start to talk about the change over the last 4 decades. So this is the percentage of the mean number of hail prone days that the change is per decade. So we're looking at a 40% increase over those 4 decades in Sydney and Canberra and in Perth. And a larger relative increase in Hobart, but from a low base point. And decreases elsewhere. So this is interesting, and it kind of goes into the other study. So this is only talking about the past, and we were really careful in this study not to suggest that this would necessarily continue into the future because we didn't know. Now we have a little bit more information on that, which I'll talk about in a minute. You might say, well, what is actually driving these trends? So what I did here was I took apart each of the ingredients for the proxy and looked at which ingredients were pushing the trend up and which were pushing it down. So in this map, the red areas are where that ingredient is increasing the trend, and the blue areas are where it's decreasing the trend. And so you see that they are mostly driven by CAPE and lifted index. Those are both measures of instability. So it's the instability that's changing. It's this moisture, the extra moisture and the larger updrafts. And where it's being pulled down, it's being pulled down by temperature changes. So this T500, that's the temperature of 500 hectopascals, so sort of mid-height in the atmosphere. And the melting level height, so it's melting level that is causing a lot of the decreases that we see, particularly across Queensland. And the interesting thing here is that the wind shear doesn't play a huge role. This kind of goes with other studies that show that wind shear changes are less important than the instability changes that we see. This goes to Tim's point here about the number of times you actually get a hail event. So we compared to radar data. So this plot in the top right shows the 2 lines, which one is it? The proxies in black, so it's higher. You get a large number of hail prone days, but maybe 10-20% of the time you actually get an event on radar, but you do see that they co-fluctuate. So this shows that the proxy is kind of picking up the same patterns as in the radar data. And spatially as well, they both show increases in the southeast and decreases in the northwest. Although radar data is hard to work with, I mean, the reason we went for the reanalysis data was that it's all estimates, but it's complete over time and space. Radar is real observations, at least something was reflected in the atmosphere, whether it was hail or a bird or whatever, there was something there. But it was over shorter periods of time, there's disagreement between the station time series and the lengths of them. So it's hard to work with, but overall, same kind of spatial pattern.
Sorry, Tim, this radar data, is that for the ingredients, variables, literally hail?
Yeah, I mean, literally something solid in the atmosphere falling. And we use a thing called the maximum expected size of hail, which says if there's ice up high and there's a power law relationship, it says if you get a lot of reflectivity up high, it's probably hail. So yeah, it is not necessarily hail, but it's something in the atmosphere that's being measured, not an ingredient in the same way that the proxy is an ingredient. Yes. So here's my conclusion for this section. Over the past 4 decades, so here we're only talking about the past, and we're only talking about frequency of hail. Hail hazard frequency has reduced across Australia overall, but it's increased in these areas in the southwest and the southeast. So now getting on to damage potential. So this is work that I've done with Joanna Aldridge at QB, and we're now looking into the future. So we're interested, and I had some fun with AI here trying to get it to, I put in hailstones with measurements of size. AI can't do numbers or writing, so it's interesting to see that it can't do it. But I liked the picture enough to include it anyway. So this is work that's been submitted to GRL, it's in review, and I'm responding to the reviews now. So the interesting thing about hail damage potential is that it's pretty much directly related to how big the hailstone is. So larger hailstones mean more damage, that makes sense. What is not maybe so obvious is that if you have wind at the same time as your hail falling, the damage goes up exponentially. And this is true both for crops and the built environment. And it's because the wind pushes the hailstone sideways. So instead of just falling straight down, they come in at an angle and they can smash the sides of buildings. And that's when you get sidings like this on the buildings smashed, as well as a lot more crop damage. So it really increases it. And here we wanted to look at both the hailstone size and the wind as well. So the motivation, of course, is that billion-dollar hail events occur. Hail events, when we look at them in the insurance record, they nearly all have a wind component as well. So there'll be notes that will state giant hail and large winds. There's always a wind component. But we really have not very much idea of how those factors are changing with climate change. So we have this downscaling study. I'll explain downscaling in a second. So here's my map of Australia and the areas that I looked at. And the coloured squares that are overlapping each other in a kind of confusing way, those are the domains of our model. And with downscaling, what you do is you take the boundary conditions, which are at low resolution, and you ask the model to use its equations to work out what was going on at a higher resolution inside that area. So in this case, we're going from the conditions from, well, it's from a study by Zhu et al. That provided boundary conditions for both a historical and a future period, where the future period had the variance of reanalysis, but the mean trend from CMIP 6. So it's got a trend on temperature, but the variance from reanalysis data. And we took those boundary conditions and we asked a weather model called WRF to downscale those to get high resolution weather maps of what's happening inside these areas. The areas cover 65% of the population because most of Australians live in cities. So we're covering Perth, Adelaide, Melbourne, Canberra, Sydney, and Brisbane. These are the more hail-prone cities. And we also covered this region here around Kalgoorlie because of that map that I showed before, which had that area of slightly larger hail risk in that region. What should I say about this? We did 2 epochs, a historical one, 20 years from 89 to 2009, and a future one from 2080 to 2100. And the difference in temperature between those in this model was about 2.4 degrees. So we're talking about 2.4 degrees of warming. And we ran this at 3 kilometre grid spacing. So if you have other questions about the model setup, you can ask me, but this is the kind of output that it gave. Here I've got for each city maximum hail sizes over the entire period, over the whole 20 years, for the historical period on the left and the future period on the right by city. And you can sort of see, especially in like Melbourne, you have more hail, larger hail occurring in the future period than in the historical period. And it's interesting to me that you do see the individual storms. And this is very much like what happens if you take 20 years of radar data and you look at where the storms went, you see the tracks of where the storms hit. So we first looked at just the frequency changes to see if it matched the study that we had over the past. Interestingly enough, it did in Sydney, Canberra, but not in Perth. So in Perth, we don't see an increase in frequency in the projections, but in Sydney, Canberra, we do. And we also see an increase in frequency in Brisbane, which in the past showed Brisbane was on the southern edge, if you remember, of a large area of decrease. I'll talk a little more about this soon, but I think Brisbane's kind of at a a funny turning point. So the uncertainty in Brisbane, I think, is higher than in other places. But we saw like a 15% increase in Brisbane, almost a 30% increase in Sydney and Canberra, and the changes were not significant elsewhere. So that was frequency, but we're really more interested in the changes in the hailstone size and the wind. So we use generalized extreme value distributions to look at this because it's a nice mathematical framework. We looked at the maximum daily hailstone size and the maximum daily wind speed at the points where the hailstones or where there was hail included. I have to say there's a bit of a wrinkle in this study here where the hail size is an absolute maximum, but the wind speeds are a maximum of hourly instantaneous wind speeds. So it's like you took a measurement of the wind speed every hour, and then I'm taking the maximum of those, whereas the hailstone is the maximum over the whole day. So we expect that the wind speeds that we're talking about here are actually underestimates of the real simulated wind speed. So we did quite a lot of analysis to work out which of these changes could be considered significant. So we looked at KS tests and we looked at the overlap in model parameters. And long story short, we worked out that although the fits were kind of reasonable, the changes were only significant in certain places. So Perth, Kalgoorlie for hail only and not for wind, Sydney, Canberra for wind and hail, and Melbourne for wind and hail. All right. One of the nice things you can do with GEVs is you can look at return periods very easily. You can just say, what is the return period for hail of 10 centimetres? So that's what we did here. We looked at 10 centimetre hail. The return period in Melbourne in our simulations reduced from 20 years in the previous time to 3 years in the future period. In Kalgoorlie, it went from 18 to 6 years, and in Sydney, a much smaller change. So the model thinks Sydney gets larger hail more often, which is true. 3 years to 2 years. We also looked at changes in threshold damage. So we said, so what is the chance of a hail day giving us a hailstone of 50 millimetres, say? That's what we call giant hail in Australia. Different in the US, by the way. So 50 centimetre giant hail, the probability of a hail day giving us one of them went from 14 to 18 centimetres, so a bit of a change in Sydney. But in Melbourne, it jumped from 9% to 24%. So quite a bigger change in Melbourne for hail size. And the 100 millimetre hail, kind of as I said already, is much more in Melbourne in the future than in the historical period. Then looking at wind damage. Oh no, sorry, this is just the other side of the continent for hail as well. So in Perth, also an increase in giant hail, but the 100 millimetre hail there actually reduced. I mean, I think it's just close to zero in both cases. So Perth does not often get very large hail, so that kind of makes sense. And then in Kalgoorlie, it's interesting that the chance of getting large hail there seems to be higher than in Perth. The chance of getting a 50 millimetre hailstone went from 12% to 21%, and a 100 millimetre hailstone was 3 times as likely in the future. Okay. Winds, though, decreased. So this is, I'm calling them hail proximal winds because they're not perfectly coincident with the hail, but they do occur within the track of a hailstorm and within 1 hour of hail having fallen. So they are proximal to hail. And what we actually saw was that in Sydney, Canberra, Melbourne and Perth, the chance of getting a 80 km/h wind gust around hail actually halved in the future. But in Kalgoorlie and Adelaide, so these more central places, it did seem to increase a little bit, but we, as I said before, don't consider those results to be statistically significant. So again, now looking at the drivers for these changes, we saw in the past that it was instability that was driving the changes, and this seems to be the case in these cases too. ML CAPE is a measure of instability. It's the so convective available potential energy for a mixed layer, that's the ML. SO6 is the shear between 0 kilometres and 6 kilometres, and SIN is a measure of the inhibition. What that means is that if you've got an unstable atmosphere, but there's actually a temperature inversion, so you've got a warmer layer of air, then the warm air that's near the surface that wants to rise can't get through it. It gets stuck, and actually a bit of inhibition increases the severity of storms because it lets the storm build up and build up and build up before it kind of explodes into a massive storm. Whereas if you just have pure instability and no inhibition, the storm can kind of release the instability over time. That was all kind of background info, but the point here is that it does seem to be the instability changes that are driving these changes. So in Sydney and Canberra, we've got really large increases in instability, moderate increases in inhibition also that could lead to more explosive development, and not very much change in the shear. But in Brisbane, and this is where I think Brisbane's kind of a case where there's more uncertainty, we've got a moderate increase in Cape, we've got a bit of an increase in inhibition, not like the other centres, but we've also got a decrease in shear. So there's more offsetting going on. So the instability increases, shear decreases, the hailstorm doesn't change very much. And I think that's probably what we're seeing here. There's just more of a tussle between those ingredients.
Great tip.
Yeah,
The grayed out values not significant.
correct. Yeah. So the only one out of these cities where there was a significant change in shear was Brisbane. The other ones had insignificant change. But we did have significant increases in temperature across all the domains, which is what you'd expect. It's a warmer scenario. Thanks. So again, my conclusion, this is the long one where I couldn't make it one sentence. With warming, the hail sizes are projected to increase in Sydney, Canberra, Melbourne, Perth, Kalgoorlie. Hail frequency is projected to increase in Sydney, Canberra, Brisbane, so slightly different. And on the other hand, hail proximal winds are projected to decrease in across the south, Melbourne, Sydney, Canberra, and Perth. But as I said, there's uncertainty around what happens between Melbourne and Perth.
A quick question, Tim. How did you choose your two periods that you're comparing, current and future? Is it robust to changes in those choices?
So I haven't tried with other periods, but I tend in these cases to try to not think about the years so much as the temperature change. So I wanted to get a good temperature change between the periods. So I just chose like a historical period and the end of the century because it would be a reasonable temperature change to work with. And I used, I think, 4.5. So that's why it's like 2 point something degrees. So, I mean, it's not like I chose those for those particular dates. As to whether they're robust, I mean, the changes kind of align with our expectations. So I would think that, and I'll show in the global case as well, when I look at say 2 degrees and 3 degrees, 3 degrees in general is just like an extension of the 2 degree change. So, yeah. So now going to global, another AI generated image, but I really like this one. So this is a study that I've done now with Raphael Portman, Chris Darius, who is around here sometimes, and Steve Sherwood, who you all know. Raphael's in Switzerland and is an agriculture and hail person, so that's really interesting. And it's why I have the crops in here. So, all right, so there's this interesting dynamic between thermodynamic changes and dynamic changes. This comes up all the time with climate change changes because the thermodynamic changes are easier to predict than dynamic changes. So thermodynamics just means it's warmer and there's more moisture, right? And it's easier to predict what will happen in the atmosphere. You kind of know that there'll be more instability, there'll be more melting. Okay, dynamic changes are changes in the weather system. So they're changes in the synoptic scale patterns, and they're changes in La Nina, El Nino, and they're changes in all these drivers that cause moisture to be moved around the world and different winds, and they're a lot harder to predict. What I was trying to do in this study was to include dynamic changes, which by the way were included in the last one too, because we used boundary conditions that included dynamic changes, and not only the thermodynamic changes. Now we're going back again. So I went from a proxy study in the past to a model study in the future, and now I'm talking about a proxy study in the future. So we're going back to proxy, so talking again about ingredients instead of hail being simulated in the model. Here's how I chose the projections for these ones, and in this case I was explicitly looking for temperature changes instead of year periods. So I wanted a 20-year period that was centered around temperature change. So I took my historical period, which is the same across all the different models that I used, and it's CMIP6, and then I found the 2 degree period and the 3 degree period. Someone asked me what this overlap color is. It's just where the two periods overlap. And so I've got 8 models which had the variables that I need to be able to do this kind of proxy study. And we've regridded them all to 1 by 1 degree resolution for aggregation so that we can talk about them all at the same time. So in the end, I chose 3 proxies. I applied a bunch of different proxies, and they're all here on the right. There's a whole bunch of them. Some of them, though, produced like year-round hail conditions across the tropics, which is obviously not true. So those tended to be the proxies that were trained high up in the mid-latitudes. So they're proxies there that were trained in Germany, for example, and they're just not applicable to the tropics. So in the end, I used my one, which is specifically designed to deal with the fact that conditions change by latitude. I used another one which produced reasonable results, but it was trained in Italy. That's the ECHL proxy. It's just a plain, straight instability shear proxy with no change by anything. Just is the same everywhere. And I'll talk more about why that's important soon. And then I used another one called SHIP, which is the severe hail parameter. I think significant hail parameter. And I used a threshold on that. It uses instability, moisture, shear, and temperature. So one thing that's really important here is that ECHL doesn't include temperature at all. It just has instability, which implicitly has some temperature in it, but there's no explicit temperature in that proxy. So all up, I had 3 proxies, 8 models, and that gave me a 24 member ensemble to deal with over the future. Just as a test, I looked at a time when we knew that there were lots of hailstorms. So this shows the year of 2022 in the reanalysis data, so only one model, where we know that there were hailstorms. And the proxies do highlight this area in southern France up here in June when there were really big hailstorms that broke records. So it does seem to, that together the proxies are able to highlight times where there was more hail activity than other times. And I tried it in India also. Both of these were cases where we applied the proxies to places where the proxies were not trained. So none of these proxies were trained in France. Seems to work okay in France, same in India. And this is the map we get of the number of hail-prone days when you sort of take the average over all those ensembles in past data. Now, the actual number here of hail-prone days, I think, has rather a large uncertainty on it because the different models and the different proxies all produce different numbers, but the pattern looks good. So we're seeing here that it's picking up areas of the world where we know that we get hailstorms. So you see the US, see the east coast of the southern continents, so the east coast of Australia, South Africa, and into Argentina from the coast. And you see Europe around the Alps, you see northern Italy, and you see Bangladesh and northern India. So you see these areas where we know that there are lots of hailstorms happening. So that kind of tick. And then this is the future projections. So this is the change in mean annual hail-prone days for the 3-degree scenario. And the 2-degree one looks like this with the colors a bit more washed out. So what we're seeing is, first of all, a lot of uncertainty around the tropics. And I'll talk more in a minute about how these proxies don't agree in the tropics. But in the mid-tropics, we're seeing that hail doesn't increase, it mostly decreases. Sorry, mid-latitudes. And then towards the poles, we're seeing increases in hail-prone days. So it's a shift from the mid-latitudes out towards the poles. And the hatched areas here are where more than half of the ensemble agreed on both the significant change and the sign of the change. So it's also a seasonal shift. And so here I'm looking at should try to move this. At the top is December, January, February, DJF, and at the bottom, June, July, August. So it's the cold and the warm season. In the warm season, you see decreases, and in the cold season, you see increases in hail-prone days. So we're seeing a kind of shift from warmer places to cooler places and from warmer seasons to cooler seasons as the temperature goes up. So here's where the proxies disagree. I've got now a column for each proxy. So this is the full ensemble and all the changes. You see my proxy and the SHIP proxy tend to agree on the direction of the change, but across the tropics, the ECHL proxy is the opposite. Okay, so this is why we're getting really large uncertainty in the tropics. Now, I think this is because the ECHL proxy is more like a traditional just storm proxy. It was trained for hail, but it doesn't have any temperature in it. And this means that the other 2 proxies, which include temperature changes, are modulating those changes. And being held back by the increase in the temperature. Whereas the air cool proxy is just like, let's go. It's more unstable. That means more hail. So we get disagreement, and the place where we get that disagreement is across the tropics. So now looking at the drivers of the changes, again, this shows red where the proxy was pushed up by the certain ingredient and blue where it was pushed down. And you can see that the instability is really pushing up that air cool proxy, and that's because it's just plain instability shear. Whereas the temperature is holding back my proxy, and it's also holding back the ship proxy also in terms of moisture a little bit there as well, the most unstable mixing ratio. So overall, these changes are driven by instability. It's the instability that makes the change happen, but then it's the temperature that holds it back in places where the temperature is going up. We were able then to talk about crops, and Raphael suggested this data set called Merca 2000, which is a data set showing the times of the year that different crops grow worldwide. It's stuck in time, so it's stuck in the year 2000. Now, I'm about to talk about how crops might be affected by these changes in hail. And I think the first thing you're going to think is, well, crops are also going to be affected by changes in climate. So cropping seasons will change. So this is a sensitivity study. It's going to show us which crops are more sensitive to changes if the crops stay the same. So I'll just put that out there as a caveat. And what I'm talking about here are changes in the proportion of the cropping season that is hail prone. So say that a particular crop grows only in winter, and I'm talking about what proportion of those months is hail prone and what proportion is not, and does that proportion change in these future projections? And I've done it by crop, so that's do all the different crops here, and then by region, I've just picked out a couple of regions to show. If it's below zero on this plot, then the hail prone proportion is reducing. If it's above zero, then it's increasing. So in Africa, we're seeing just widespread decreases in the number of cropping, the amount of the cropping season that would be affected by hail in the future. In Europe and in Oceania, we're seeing changes that depend on the crop. Now I'd like to go into why that's the case. So it's effectively the seasonality of the crops and the fact that these changes that we're seeing are most concentrated in the cooler months, and the increases we're seeing are in the cooler months and the decreases we're seeing are in the warmer months. So here we have the month of the year, the 3 proxies showing the hail prone days per month, and this is for the change in the amount of the hail season that is in the future scenario. So if it's above zero, it's an increase. If it's below zero, it's a decrease. And you see that in the summer months, we get this disagreement between the proxies, and that's because of the differences in the proxies that I just talked about. But in the winter months, we see increases in the number of hail-prone days where the proxies agree. And then at the top of the plot, I've got the months of the year that are where those particular crops are growing. And so the crop that is most affected is barley, because it is the crop that's growing in winter, whereas the other crops are growing year round, and the changes kind of get bit. So overall, the winter crops are going to be most affected by increases in the hail hazard, and the summer crops are the ones that will be most affected by decreases in the hail hazard. Okay, my conclusion, 2 sentences. We're projecting a poleward shift in hail frequency in the future, so moving out towards the pole. Temperature changes are really important, and this is why I think it's important to use proxies that include temperature changes for hail instead of the proxies which are just instability shear and only have the implicit temperature. I'll just add that the uncertainty is higher in the tropics than in the mid-latitudes. All right, so now just coming to my conclusions. We're making some progress, but the uncertainty still remains really high. But I think now we're starting to get a little bit more of a picture of what's going on in Australia. So we're sort of getting glimpses through the fog of, well, we've got an improved climatology and continental trends, and now we're getting glimpses that there might be increases in frequency in the southeast and decreases across the north, driven by changes in instability. Increases in hail size in the southeast, and then worldwide, this indication of a poleward shift in frequency. So I'm going to finish up there, but I just want to make a little add. It's a little bit cheeky of me, but we're running a workshop later this year on severe convective storms. Thanks very much to the ICRR, who's really helping out, and to QBE, who's sponsoring. It's going to be on the 7th and 8th of August here at UNSW, and we've got registration and abstracts now open, and the website is unsw.to/storms. I'll leave this one up here and take any questions. Thanks.
Hey Tim, really interesting. On the last paper, I obviously don't have knowledge about hail, but hear me out. So you have a variable of interest, which is ice balls hitting the ground, right? But you can't, it's hard enough to observe that historically in a consistent way or, in a good way, and let alone predicting it with a climate model.
Yeah.
So you're using a proxy instead.
Yeah.
And to train the proxy, I'm assuming you're using historical data on the ingredients and how that you estimate a function that maps that to your variable of interest.
Yeah.
Now, to do this forecasting, I think you have to make the critical assumption that this function that maps historically is going to remain the same under potentially severe warming
Yes.
of the climate. And you convinced me that hail is a very complex process with, a lot of things going on.
Yeah.
Is there any good reasons to suppose that that assumption is going to hold, that this function mapping the proxy to the variable of interest is going to remain stable
Yeah.
in the future?
That's a really good question. And I think it is a problem that we have. It's certainly an area of uncertainty, like whether that function is stationary and whether it's going to change. What I kind of go back to is in the training data, say for my proxy, we used a whole range of different conditions. We used data that was all across Australia, and the different climate zones that are in Australia have really warm zones and really cool zones. And so I have kind of at least some level of confidence that that proxy is able to deal with different climates. And the fact, of course, that it seems to work across the world in these sort of warmer and cooler regions gives me some level of confidence there. But yeah, it's an issue.
Did you try looking at in the historical data whether there was any evidence that the function changes over time? You have 1.5 degrees of historical warming. That could be.
Yeah, that's a good idea. No, I haven't tried. Yeah, but a good idea. Yeah.
In your WRF simulations,
Yes.
how do you represent the cities, and do you think it matters?
Yes, it matters. And cities are just basic wharfs, so they're probably what they are, just rock. So this is, I mean, you talk to Negan Nazarian, who knows all about this. Cities are really important. And at the moment, we have an honours student, Ebony Mackin, has started, and her task is to look into exactly this question of how much the cities matter.
So they may not even be rock, they might be beautiful broadleaf forest.
Yeah, absolutely. It's a real issue. But Ebony's project hopefully should shed some light on how much it matters.
This might be the same question that Andy just asked, but I guess what I was wondering is how much of the hotspots over cities is coincidental or unfortunate? Is that the same question?
Yep, it's certainly a very similar question. I think like when you look at our maps of trends, for example, the regions where you see increases, so people have said to me, are those increases because we've got cities there? I don't think so. I think the trends are too widespread for it to really be the city influence, but I am convinced that the cities with their heat island and their change in wind circulation would have an effect on hail. So again, this is what Ebony's going to be looking at to kind of quantify that effect. And then the question is, are our cities exacerbating the hail risk? That's one question. And then if so, what is causing that exacerbation? And could we design our cities in a way that would reduce hail risk? That's a long way down the line, but
is there evidence from other parts of the world that
there's evidence that, there's some small number of studies that the heat island effect plays a role. Yeah, you get more convection over cities just because there's more heat there. But the wind effects, I think, are more complicated and harder to tell. And there's only been a couple of studies in Australia. I think Andy was involved with one in Australia that showed a peak of convective activity over a city region when cities were properly mapped.
They're also aerodynamically rough.
Yes.
So if what's driving this trend is instability, they might amplify that instability.
Two questions.
Okay, I can actually see. So first question, Matt Mason. So hi, Matt. That says, how useful do you think your model estimate of wind speed associated with hail is? Most significant damage of hail and wind is when hail is driven by RFDs or other storm-specific winds that won't be simulated with high fidelity in your model. Yeah, so the model hail fidelity is not as good as the model wind fidelity is not as good as the hail. Part of that is resolution. We're only at 3 kilometer resolution here, so we can start to look at hail expectations at the ground, but the wind, yeah. I think what we're doing is we are significantly underestimating the winds that are in that model. And part of that is the model setup, and part of that is the fact we're only looking at hourly winds. So I think, yeah, there's quite high uncertainty on those winds. And I'd want to look at something a lot higher resolution to actually look at gusts. So I hope that answers your question. And then the other one is, for the WRF simulation, did you test if the innermost domain resolution would affect the result, like 3 kilometers versus 1? That's also a good question. So I chose 3 kilometers partly for computational reasons, just because it's cheaper to compute than 1, but also because Hailcast was designed for a 3 kilometer domain, so it seemed to make sense to use that. Would it be affected? I think it would affect the wind, the fidelity of the winds, but I'm not sure that it would affect the signal that we get. And for hail, I mean, I don't know because I haven't tested it. My guess is that you might get some higher peaks of higher hail just because you'd have higher resolution, but that overall the signals will be the same. But I haven't tested it.
This might be a bit of a tangent, but how close are we to being able to forecast in a weather or seasonal climate sense, forecast these hail ingredients like the inhibition, the instability, the wind shear? Is that getting anywhere close to the point where farmers could make decisions on whether it's worth getting the harvesters out early and maybe sacrificing a bit of crop quality, but just getting it in?
Yeah, so you're talking about seasonal prediction.
Yeah.
Seasonal prediction is hard for this kind of stuff. What we are trying to do is to look at links between larger scale drivers, like ENSO, and the number of hail prone days you get. And we're starting to see that there are some links. There's a published work showing there's a link between ENSO and hail in Brisbane. And there's a study that's now by Forrest Tutt, who was an honours student. He looked at this question and found some correlations. That's going to be published soon. And then Boris, who's a PhD student, he's looking at interannual variability, and his first task is to see what he can do with seasonal, well, not seasonal prediction, but correlations between these drivers and hail occurrence. So at the moment, not so much, but stay tuned.
Cutting edge. Yeah. Okay.
All right, should we leave it there? Any more questions? Okay, well, let's thank Tim again for a fascinating talk. To the next seminar, which I think might be out.